So, considering that an extraterrestrial civilization would have to be far more advanced than ours, they would have to have the energy, the tremendous amount of energy coming in the form of propulsion and giving their spacecraft velocity to get here. We should detect a signal of tremendous powerful energy. Where would we detect such a signal, and how would we detect it? So far, cameras and telescopes and other means of making detections, such as radar, are limited to the electromagnetic spectrum. Light, in the form of photons or waves, bounce off of solid objects. If this was an apple or an orange, you would see photons doing the speed of light, bouncing off of that, so that we can observe phenomena happening right in front of our eyes. So we observe everything in regards to the speed of light. If we were going to actually see a spacecraft that could come here from such great distances and be able to even go way beyond the speed of light, we should be looking at something so powerful, something that we had never seen before. And I suspect where we should look is in the upper part of the electromagnetic spectrum. So for the next part, we're going to actually look at what the electromagnetic spectrum is and what light is, so we can see where the best place to actually detect a signal from a spacecraft would be. So what is light? Light, in effect, is actually just energy, vibrating in different energy spectrums. I've made a chart here of the electromagnetic spectrum, what is known as the electromagnetic spectrum. And we can see, basically, from the diagram, that light is just energy in the form of waves. And these waves, as we go higher into this energy spectrum, start to oscillate faster and faster and faster per second. It was Heinrich Hertz who identified electromagnetic waves as Hertzian waves. Every single second you could produce one oscillating wave, you would have 1 hertz. And the higher you would go into this spectrum, you would get more and more and more oscillations per second in this wave. In fact, this actual chart here is not very accurate, because even when you get into the radio and television spectrum, Hertzian waves are oscillating in up to the millions of times per second. But anyway, Max Planck, the godfather of quantum physics, was the first physicist to come up with an energy formula in regards to the electromagnetic spectrum. He said energy was equal to the frequency with which these waves or quanta of light oscillated. So the more oscillations per second that occurred in a wave, the greater the energy was present. Einstein won the Nobel Prize in 1921 for explaining the photoelectric effect. The photoelectric effect is essentially the conversion of photons, the mass particles that are basically light, and converting them into electrons, which is energy. He discovered that when photons struck a metal plate or a conductor, the metal plate ejected an electron. So when the photons, which are light particles, came into the object, the conductor ejected an electron, and that electron had a charge on it. So what that showed is that photons, light, had energy in them, and that light could be converted into usable electricity. Well, when we consider again the equation of energy in relation to space travel, and that we needed this huge amount of energy in order for a spacecraft to do the speed of light, many problems arise. Einstein said in his formula E equals mc squared that as a spacecraft or any mass object tried to approach the speed of light, the impeding forces of inertia became so great on that mass that the amount of energy required had to increase proportional to how fast you were going. Eventually, Stephen Hawking wrote of Einstein's equation that the problem with attaining the speed of light for any spacecraft would be that as that spacecraft tried to reach light speed, its mass would increase so much that an infinite amount of energy would be required for the spacecraft to attain the speed of light, and therefore it could never actually attain the speed of light. So, energy is the big problem. We need tremendous amount of energy for a spacecraft to do the speed of light, and if we were going to detect a spacecraft that had the kind of energy required to go the speed of light, it should be detectable somewhere, we would hope, in the electromagnetic spectrum. Today, most of our cameras look in the visible light spectrum right here. This is all we see with our human brains. So this is what we know of light today. There are radio and TV photons. There are microwave photons. There are infrared photons detectable usually as heat. Some snakes and reptiles can actually see in the infrared, but our eyes can't see that low in frequency. Then there's the color red. Red is actually a frequency of energy. It's actually a frequency of energy wave. And the color orange, and going all the way up into green, into blue, into violet. Violet is the most energetic color that our brains can see, and most of our cameras can see. Above violet is ultraviolet, and ultraviolet light is divided into near, far, and extreme. So the ultraviolet bandwidth, as we know it, actually extends a little further than my diagram shows here, but basically goes 5 or 6 times the bandwidth that the human eye can see. So again, if we can observe and take pictures into these higher spectrum, what we are actually seeing in that spectrum is more energy, actual energy in the form of electromagnetic waves. When we take a picture in the X-ray spectrum, we're actually seeing energy. And by the time we get up into gamma rays, we're seeing a tremendous amount of energy in the form of an observation. So again, if a UFO were coming here from another planet, from another star system, and we were expecting it to have a tremendous amount of energy to allow that spacecraft to conquer the vast distances of space in very little time, we should be detecting something that should be way up into at least the visible light spectrum and even higher. So far, SETI, the Search for Extraterrestrial Intelligence in Mountain View, California, uses a vast array of radio telescopes to try to look for intelligent signals in the form of radio signals or TV signals coming from another planet or another star. And if we receive such a signal, such as in the movie Contact, you would expect to see an intelligent signal in the form of a radio or TV wave. But so far, that effort has retrieved nothing. I believe the reason they haven't found anything down here is because there's not enough energy down here. They forgot the energy part of the equation, that it takes energy to get velocity in the form of propulsion to get here. And even an intelligent signal coming from another planet would require tremendous amounts of energy. So I believe we should be looking at least here in the visible light spectrum, and we have. There have been many alleged reported sightings of UFOs in this spectrum because that's what we see. But in my philosophy, when I consider Einstein's law, E equals mc squared, that mass cannot attain the speed of light because of the forces of resistance and inertia, I would expect a spacecraft to be pure energy, something that is not even physical as we know it, something that would be matter vibrating in a very high frequency state. And basically, we should be looking for a craft that looks like an energy ball or an energy wave, and that energy wave should be a very, very energetic wave that should only be detectable in these upper spectrum. So what I started to do is to see where was NASA looking. NASA knows the same thing I'm telling you. Space scientists know the same thing that I'm telling you. Where are they looking? And what I found out was the space shuttle's video cameras were looking into these upper spectrum of light. In fact, the video camera on the space shuttle can see near ultraviolet photons as well as the visible light spectrum. And this is exactly where we would start to see something with a tremendous amount of energy. Say this was the UFO here, and it wasn't visible down here. That would tell me, if we were detecting something here, just to start with, that object would be a very, very high energy object. It would be a quantumized, phenomenal aircraft or spacecraft. And there would be nothing physical about it. It would be pure energy. In fact, we should be looking for a spacecraft that is made of pure energy. And what you're about to see in this investigation is black and white video footage taken from the space shuttle throughout the 1990s, and a camera that is capable of seeing into at least the near UV spectrum. So if some of these objects that we see in the tape were not visible to people's naked eyes down in here, it should come as no surprise. We're looking at high energy phenomenal objects.